Welcome. So what I'm going to be talking today is a work that we are doing in Santa Cruz. And it's how to build agents for chip design, hardware agents. A little background to see what we are doing here. I'm a professor at UC Santa Cruz. My background is computer architecture, so chip design. But I always have been doing how to improve the productivity. Obviously, that includes design, verification, different aspects of the chip design. But today the focus is AI agents, how to build agents to help me improve productivity at this globe. Now, obviously, this is a work for a lot of my students, myself, that's my Git commit history. I like to work too on the code. So what's the goal? Because I think it's important we set the goal, what I'm working about. So the idea is to improve chip design productivity. And this includes the coding, the verification, a lot of effort on optimization parts. And there can be some cloud, either CLI kind of interface, and this is something we are working on. It's not how to integrate AI on the EDA tools. There's a lot of people working on that area. It's a different community. Here is how to improve the productivity, much more like what we are talking here at the conference. Because it helps you to understand how do I approach the problem and what do we do. I think it's important to what is my view on LLMs? How do I see them? How do I use them? In a way, they are sort of an alien intelligence. So they are better than humans in some things. So they are better as excellent translators. So they can translate to English, French, much better than me. They have excellent recall, or not excellent, but very good recall, much better than humans. But in some way, they are worse than humans in consistency. They have maybe not very good term, but funny failures. They have many strange failures that you have. So how I'm gonna make it work with this? Well, the first thing is I'm not going only the LMs, I'm building on agents around. So the agents, I tend to call it many times grounded agents. I tend to call it more verifiable agents whenever I can. The idea is that we always have coupled the LLMs, whatever we use, with checks, and whenever possible, we verify. In hardware, we can verify many times the results. So what we keep doing is building pipelines in which you can have an output of the LLM, and then you check if the result is correct. If not, you keep going back and you keep iterating. Because we have these verifiable agents that we can build, so we can iterate and go towards a better solution. So we check with the EDA tools whenever possible, like do we have mistakes, like combinational loops? Do we have things that they shouldn't be happening there? And if we have a verification infrastructure that usually in hardware you tend to have it because it's very expensive to do a mistake. So then you can check with the verification infrastructure. Whenever possible, you validate with previous results. Many times you are doing optimization, you are just transforming the code to get better quality code. So in that case, we can use formal tools to formally prove that the code is equivalent, even though they look very different. So at the end of the day, there are many blocks, and it looks like a compiler. So you have blocks that have the typical React loop, so you can have some reasoning to expand. You might want to extract inputs and outputs, and you have a compiler-like flow. So what makes hardware special is that it doesn't work with a normal, Python is a von Neumann architecture, hardware is not when you program in hardware. And there are many issues. Not von Neumann, pipelining is a very specific way of parallelization that the LLMs don't have very good training and they do a lot of mistakes. And there are a long list of the slightly different on the programming language. But for the non-hardware people, I have a little slide. So if you were having a program like this, you say the result of C is the result of multiplication A and B, and then you write assert that C is the result of the multiplication, and let's assume that this does multiplication. In hardware, this can fail. And the reason is because the result might not be this cycle, might take 2 or 3 cycles later. So there are a lot of checks that you might have to do that the code generation on the LLMs don't have that assumption because there is not enough training set for this type of languages. So how do we do? Because it's a short talk, I'm just going to show you a high-level view what is the idea. So we have two programming languages. One is Verilog, the other one is Chisel. So how do you do a reverse pass? So you can build a compiler-like infrastructure, putting the LLMs in the middle to solve this, and at the end there is no hallucinations because you formally prove that the result is correct. So what do you have? You have original Verilog, you have a fixed Verilog, so you have a change, and the original Chisel. You want to have a patch on that Chisel. Now, the first thing, you have to narrow the space because those files are gigantic. So you do a diff, like a fuzzy grep kind of thing. Then you can start to filter per tokens. Then you match where is the likely sources. You have to guide the LLM because you provide the whole thing, it's not going to work. You provide likely sources where you have potentially problems. And you have a hint of database of things that you have been solving before in similar experience. And then you generate many patches. No, just not to fix one, you generate many, and you change the temperature, you try to play to different variations. You compile and you have a React loop. Then LEC is logical equivalent check. It's a formal equivalent tool pass, so you can formally prove that they are correct. And then if it gives you the answer, you know, I fixed the Chisel and it's correct, and I don't have any problem. Now, if it doesn't give you an answer, then it's like, well, let me expand the search, let me try it. But at the end of the day, you may have, I give up. So how does it look when we try with different LLMs? So it depends on the results, but around 80% of the time, we're able to fix the bugs. We're still working on the type of bugs because the question is how do you add the bug? Many of the bugs, we change the Verilog, but then we, as humans, we don't even know how to fix the Chisel unless we blow up all that section and then suddenly we start to fix. So many of the bugs that we have added, we don't know how to fix them. So we have to see what is a fair comparison. But in 20% of the time, we say, no, sorry, we cannot fix it. The idea is that this is just an example. There are several other flows that we are building like that. Different flow, different pipeline, different idea, but it's the same. So what are the things we are having? We're working on open source, so you can check it, but because we are as active research, is careful with the repository. You need to have on this is our second version, because in the first version, the students were doing a lot of benchmarking, consuming a lot of tokens. And things that we did is like we start to put incremental step parts. We enable caching. The steps are hermetic, help us to debugging. So we are working on a Docker integration. So there are a lot of little things on infrastructure that makes the thing more useful. And we have some other work in progress. If someone is interested in talk to me later. But we are trying to look at things like Verilog format, formatting Verilog, improving frequency. I have 2 students working on this. And the debugging loop. So you have a long verification and then debug it. One thing that is a challenge for our community is that the tools are very slow. So the incremental part is a challenge for us. Like, as a reference for people who have not used synthesis tools, it's not uncommon. It takes 48 hours to compile. So to give you the GTS, which is the final result before the chip to get information. So it's a very slow flow. So in conclusion, we are working with hardware agents, exploring chip design, still deciding how to interface. I keep playing with different things. I keep using cloud code, like MCPs. I think the ways to go there, but we're still not convinced how to break down the pieces or not. I'm searching for collaboration and feedback, and if you want, send me an email. Thank you.